Electric current is the movement of electric charge through a conductor. Current intensity, measured in amperes, is defined as the rate of charge flow with respect to time. Conventionally, current flows from positive to negative. Current density vector J represents current flow per unit cross-sectional area measured in amperes per square meter. It's defined as the product of charge density and velocity. The total current equals the surface integral of J over the conductor's cross-section. The principle of charge conservation states that electric charge cannot be created or destroyed, only transferred. This is expressed by the continuity equation. In stationary regime, the divergence of current density is zero, meaning no charge accumulation occurs. Ohm's law relates current density to electric field via conductivity. The microscopic form is J equals sigma E, while the macroscopic form is V equals IR. Materials have different conductivities, ranging from highly conductive metals to insulators like glass. In a stationary regime, resistance depends on material properties and geometry. Resistance equals resistivity times length divided by cross-sectional area. For resistors in series, resistances add directly, while for parallel connections, their reciprocals add. The Joule effect describes the conversion of electrical energy into heat. Power equals voltage times current, or resistance times current squared, or voltage squared over resistance. This principle is used in heaters, incandescent bulbs, and many other applications. Generators convert various forms of energy into electrical energy, producing an electromotive force. EMF represents energy per unit charge provided by the source. Examples include batteries, dynamos, solar cells, and thermocouples. Receivers convert electrical energy into other forms, producing a counter-electromotive force that opposes the applied voltage. The terminal voltage equals the counter-EMF plus the voltage drop across internal resistance. Examples include motors and electrolysis cells. Electrokinetic dipoles come in two forms, active and passive. Active dipoles, like batteries, provide energy to the circuit with voltage equation V equals EMF minus internal resistance times current. Passive dipoles, like resistors, only consume energy with voltage equation V equals R times I. Kirchhoff's laws are fundamental for circuit analysis. The loop law states that the sum of voltages around any closed loop equals zero. The node law states that the sum of currents entering a node equals the sum leaving it. These principles to analyze complex circuits. Circuit theorems simplify analysis of complex circuits. The voltage divider gives output voltage as a ratio of resistances. The current divider works similarly for parallel resistors. The superposition theorem states that in linear circuits, the response to multiple sources equals the sum of individual responses. Thevenin and Norton equivalences allow complex circuits to be simplified to a single source and resistor.